Hello, my name is Aaron McCully,
I'm Calysta McKinney.
And I'm Noah Williams.
and we did problem A of the semiode. We looked at Kleptotrichy in different species of birds. For the outline of this presentation, we're going to be going over research questions, existing research, which includes both data that we were provided as well as found, assumptions, theoretical models, evaluation of these models, and lastly, conclusions and limitations of our findings. For research questions, in approaching this problem, we focused on the fact that the primary benefit for birds was using hair in their nest as insulation. We will keep this in mind when comparing the results versus the risk of hair stealing, as well as when looking at other possible benefits.
So the research questions asked us to assess kleptocracy and its risk, and we took risk to be predator involvement. And as we can see from the study from 2020, human hair had little effect on predator involvement. I'll get more into that in our assumption slide. And then we also see that the current data on kleptocracy is not significant enough to be relevant for modeling yet, because only one bird was found to pluck hair from the data that we used. So we just didn't find it significant enough to include in our modeling. So for the assumptions, like stated previously, we assume that the hair plucking is insignificant. We also assume that there is no predator-prey relationship, and we base this off the fact that the human hair didn't deter predators. So we also just assume that the animal hair will not deter predators as well. We also assume the birds want to reduce the change in heat transfer from their nest to the environment, assume the nest exposure area stays constant, and the safe nest temperatures are consistent across the world, assume the population for birds is consistent across region, and then assume volume for the nest stays constant. We also want to assume that the thermal conductivity of human hair is the same for animal hair, which is going to be 0.37, and then assume that the general population of birds will have an ideal nest temperature of 37 degrees Celsius.
For our theoretical models, we based it on three core ideas. First is Newton's law of heating and cooling, where Q prime, the change of heat with respect to time, is equal to K times the difference between the object, in this case the nest, and the environment. Heat transfer as a function of density, where we have K is equal to the volume over the heat transfer coefficient, and the hatching percentage as a function of change in nest temperature, where the percentage of survival is proportional to 1 over the change in temperature. For Newton's law of heating and cooling, we derived our equation from the temperature as a function of time, where the temperature of the environment plus the change in temperature times e to the negative kt. This can be written as Q prime equals V over our mass times the constant times the difference between the nest and the environment, where Q prime is the change in the nest temperature with respect to time, K is the efficiency of the hair insulation, T is the temperature of the nest, which we assume to be 37 degrees Celsius. The T environment is the temperature of the environment, again in degrees Celsius. V is the volume of the nest, and M is the mass of hair used.
So the temperature between nests is assumed to be a constant 37 degrees Celsius, or that's required for a safe nest. So this means we only have two components of Newton's law that have to change, and those are going to be the heating transfer coefficient K and then the temperature of the environment. So we see that K will actually depend on the amount of hair present in the nest. And in order for the temperature to be ideal for egg hatching, we actually find that the amount of hair in the nest must be inversely proportional to K. This brings us to our model for K, which shows that K is inversely proportional to density. And we can see that volume, which is a constant, is divided by mass times our heat or thermal conductivity constant. And this will mean that the more hair that's added to the nest, or the greater the mass that's added with a constant volume, the more that K will decrease.
For incorporating risk, assuming there is no predatorial risk, we see that the percentage of hatched eggs is inversely proportional to the temperature transferred. We see that the lower the temperature change, the higher the percentage of hatched eggs. For hair and hatching percentage, K is proportional to 1 over the density. Here we can see that P is proportional to the density of hair in the nest.
To look at our model, we needed to test with different climate zones and corresponding temperatures. Here we can see 2 diagrams of the globe and the corresponding temperatures. The climate zone's latitude and temperature are drawn out here. We can see the whole Arctic, subtropical, subtropical temperate, temperate, tropical, and tropical subtropical climate zones, their corresponding latitudes, and the corresponding temperature ranges. We use these values to test our model. Our first test was with the yellow-cheeked tit from Asia. Here we see that Q prime is equal to V over our constant times the mass, and then in parentheses, we have there the 37 minus the 20. We assumed the subtropical latitude of approximately 23.5 to 30 degrees and an average day temperature of around 20 degrees Celsius. From this model, we can see that the larger the mass becomes with a constant volume, the lower the change in temperature. Because P is proportional to 1 over the change in temperature with respect to time, the smaller the change, the larger the percentage of hatched eggs. We again tested our model with the tufted titmouse, which was the bird that we saw that stole hair from the research article. For this, we used a subtropical temperate latitude of 30 degrees and an average day temperature of approximately 15 degrees Celsius. Again, the mass of the hair needs to be larger with a constant volume than the yellow-cheeked tit in order to lower the change in temperature. If not, the larger, the smaller Q prime value will lead to a lesser percentage of hatched eggs.
For our conclusion, and for risk, we saw that from the data provided, there was a relatively low risk in stealing mammal hair. Out of all the different mammals that the bird stole from, there was only 1 instance of aggressive behavior, so we determined that the risk was low. For benefits, the greater the amount of hair in the nest, the greater the percentage of eggs hatched, meaning a greater survival rate for offspring. Additionally, plucking hair directly from mammals will yield more hair than finding it stray in the environment, so it will take less time to gather an adequate amount of hair needed for the nest.
Here's our citations and the resources that we used, and thank you very much for listening to our presentation.
Thank you.